So in this lesson, we're going to continue our discussion of acids and bases. Today we're going to look at a couple different theories of the way acids and bases behave. Up to this point in time, when we've talked about acids and bases, we've discussed them in terms of what's called the Arrhenius theory. The Arrhenius theory of acids is that acids are chemical species that give up or donate hydrogen ions to a solution. Usually that solution is water, but not all the time. Now, a hydrogen ion is a proton. So you could also say that an Arrhenius acid is a chemical species that donates a proton to a solution. If we were to write a chemical equation to represent the way that this works, let's start with a strong acid like hydrochloric acid. We're going to dissolve it in water. And in this water environment, the hydrogen ion, which is also a proton, is just simply going to be dissolved in water. Then in the Arrhenius definitions of acids and bases, the bases are considered those species that donate hydroxide ions to a solution. So something like sodium hydroxide does this. When we were doing complete and net ionic equations, we dissociated sodium hydroxide in this fashion and put that into a complete ionic equation and then found the net ionic equation. So we're really just doing the same thing here. The difference for Arrhenius is that if what's being dissociated or broken up or ionized includes a hydroxide ion in those products, then that's a base. In the Bronsted-Lowry concept, the hydrogen that leaves the acid doesn't just exist in this solution. It actually goes and joins up with something. So in a Bronsted-Lowry theory, the definition of an acid is a chemical species that donates a proton to another chemical species, forming a covalent bond. So let's look at it like this. Here's our hydrochloric acid. So we're not talking about different chemical species that can either be an Arrhenius acid or a Bronsted-Lowry acid. We're talking about acids that can be defined in a different way. And what we have here is, this is a limited definition of acids and bases. Bronsted-Lowry broadens that definition to include other things and explains more about how it works. So here's our hydrochloric acid. Here's the water. And instead of saying the hydrogen ion from the acid just simply goes into solution, we're saying it leaves this chemical species. So it does break up just as we wrote it up here, but the hydrogen ion actually goes over and joins up with, covalently bonds with this water. So the hydrogen ion is leaving the acid and going over here and joining up with the water. Now, how does that do that? That hydrogen ion wants to have a pair of electrons. It is covalently bonded to this chlorine, so there's actually a pair of electrons in here. If we were writing the Lewis dot formula for this, we'd see that. Well, the water has a couple of lone pairs to spare. Hydrogen wants a pair of electrons, and it can get it by covalently bonding right there. And we end up with hydronium, that is formed. So over on this side of the equation, we're going to have H3O with a plus charge. That's what this is. H, or hydrogen, covalently bonded with a pair of electrons to oxygen in all three places, plus that lone pair up there, and we get this formula. This is an aqueous ion, and we also have chlorine. Now, that doesn't mean that sodium hydroxide is not also a Bronsted-Lowry base. In the Bronsted-Lowry concept of acids and bases, a base is anything that accepts a proton. So the proton that left this hydrogen went over and joined up with this water. That makes water a base because it accepts a proton. Now that doesn't mean that this hydroxide, this sodium hydroxide, is not a Bronsted-Lowry base. It is. Bronsted-Lowry is extending the idea of bases to say, once we dissociate and form hydroxide, then what happens? Well, in the Bronsted-Lowry concept, if we have hydroxide and we put it in solution with an acid, let's just use hydrochloric acid here. Then when the hydrochloric acid dissociates and we get this hydrogen ion, it's going to want to go over here and join up with this hydroxide. And if we look at its structure, the hydroxide has 3 lone pairs of electrons and an overall negative charge. The hydrogen ion that comes from this acid here, this hydrochloric acid, wants to join up with one of those pairs of electrons. And the result is that we get water. So we have water, and we have a chloride ion. So now this is the base because it accepts a proton. This is the acid because it donates a proton. For every acid in the Bronsted-Lowry system, we have a conjugate base. Whatever you have left after the proton leaves, that's the conjugate base. There it is. Acid, conjugate base. And the base, which is the thing that accepts the proton, has a conjugate acid. Whatever is formed when the proton covalently bonds with it, that's the conjugate acid of the base. So that's the base, there's the conjugate acid. Base, hydrogen joins up, conjugate acid. So water is both a base and an acid in the Bronsted-Lowry theory. So let's look at what happens when we neutralize these kinds of acids. Okay? Have a strong acid, hydrochloric acid. Whether we're talking about the Arrhenius or the Bronsted-Lowry, we're going to look at what happens as we neutralize those. So what I have here is a acid titration curve. Okay? And since we're working with hydrochloric acid, it's a strong acid. And we're going to add base solution to that. So I'm starting with a concentrated HCl solution, and I'm adding base solution to that concentrated HCl solution. So the HCl solution, when there's no base added, has a really low pH. And we can have actually a pH that's below 0. We're going to start at 0. And if we add more base solution to it, the pH starts to rise. At a certain point in this process, the pH curve actually starts a steep increase, kind of like an F-16 leaving the deck of an aircraft carrier. It starts off the end of the aircraft carrier kind of just slightly up, and then suddenly it shoots up, going almost straight up into the upper atmosphere, into an attack mode or a patrol mode. So as we reach that point where the concentration of these hydrogen ions in the water is equal to the hydroxide ions from the base solution, then the curve, instead of starting to go up or making this curve upward, it starts to curve over again, and we get this sort of shape. We never quite get to 14. Okay, so 14 is the upper limit. It never quite gets there. Now there's a point right here where we're talking about where those hydrogen ions and hydroxide ions are in equal concentration in the solution. We have what's called an equivalence point. And that's a very important point to know about when we're trying to figure out the concentration of an acid, whose concentration we don't know as we start. Now that's the way it looks for a strong monoprotic acid. Let me define monoprotic. Monoprotic is an acid that only has one hydrogen that can be removed in this acid-base process. It's called an ionizable hydrogen. So if I only have one ionizable hydrogen, as I have here, then it's a monoprotic acid. An acid that has more than one of these hydrogen ions that can be removed in this acid-base or dissociation equation, this dissociation process, this reaction. If I have more than one, we call it polyprotic. Or if there are two of them, it's diprotic, or three of them, it's triprotic. Let's go back to our equations now and look at the Arrhenius theory as it applies to these polyprotic acids. Let's start with a diprotic acid, and this is the only diprotic strong acid that we deal with in high school chemistry. It's sulfuric acid. Now the hydrogens that come off, and there are two that can be dissociated. There are two ionizable hydrogens here, but they don't come off at the same time. They come off as separate steps, so we need separate equations for that. So when the first hydrogen comes off, we get a hydrogen ion, just like we got up here. And if you take one hydrogen from this, what remains is another hydrogen and this sulfate ion. And that one hydrogen with the sulfate ion has a negative charge, and that's called hydrogen sulfate or bisulfate. So here's our hydrogen sulfate or bisulfate ion. Now this is also an acid. It can also lose that hydrogen. That's an ionizable hydrogen there. So we start a new equation. We put it in water. We get a hydrogen ion. But now instead of having a hydrogen on the front here, we're going to have just that SO4. Since we removed a positively charged particle, this proton, there's an extra electron left back, so this is a sulfate ion with a 2 negative charge. So we have two equations, two different equations that apply to this. Now, in reality, this is a weak acid. And a weak acid doesn't completely dissociate. And that's what we often call a weak acid. In fact, there's an equilibrium being set up here. Instead of saying that it doesn't completely dissociate, another way of thinking about it is that all these hydrogens can dissociate, but most of them don't dissociate at any given point in time. At any given point in time, there are a lot more of these things than there are of these things. The reaction is actually going in this direction, but these two ions are joining up to reform this. So we've actually got two reactions going, one forward, one back. And the point at which the forward reaction equals the rate of the reverse reaction, we've got that balance. The amount of this or the concentration of this stuff doesn't change. The concentration of this stuff doesn't change, but there's a constant change from this to this and back again. So that's what Le Chatelier, the Le Chatelier theory, as it applies to chemical reactions, in particular, the dissociation of an acid, a weak acid, that's how it applies to this. If we do something to unsettle the balance, like adding more hydrogens or taking away hydrogens, then the whole equilibrium is shifted to accommodate for that. Take away hydrogens, more of this dissociates to make more of that. All right, now let's look at how that looks in the Bronsted-Lowry theory. So here's our sulfuric acid. Remember, in the Bronsted-Lowry theory, the hydrogen just doesn't come off and sort of float around in the water. It actually joins up with, covalently bonds with something else. In water, if we're just dissociating the acid, it's going to join up with a water molecule. So here's the water molecule. And this hydrogen is going to come off of here and covalently bond with one of the lone pairs of this oxygen in this water. And we get hydronium. And this bisulfate or hydrogen sulfate ion. Now you need to know the name of this. This ion right here is called hydronium. It's a special name we have for this. Okay? Then this becomes a new acid in the sense that it's going to lose this hydrogen. It's going to dissociate that hydrogen. And we get hydronium again. We don't add another hydrogen to this. That can't happen. We have to add a hydrogen to a new water molecule. We don't put this hydronium here in the formula. We put a new water molecule in. There's plenty of water molecules around for this to happen. But we can't add more than one extra hydrogen to the water molecule. It just won't happen. So this loses that hydrogen to the water. The water becomes H3O or hydronium. And we get this time that one last hydrogen's gone. Now we have SO4. We had a negative charge here. Removing a hydrogen ion to make this means we've left behind an extra electron, one more electron. So instead of a 1 negative charge, This is a 2 negative charge on this. Now again, this is a weak acid. And while we think about it as being a weak acid because it doesn't completely dissociate, in fact, all of it's dissociating at different times. But the rate at which these things are re-reacting and going back in the other direction, so the hydrogen's coming off of this, joining up with that, remaking this stuff, hydrogen leaving this leaves also this, the rate at which these two reactions, the forward reaction, the reverse reaction, when they reach that point where there's an equal amount going both ways, we have the equilibrium point for this reaction. Now let's look at what that means in terms of that acid titration curve. So this time, instead of hydrochloric acid, we're going to have sulfuric acid. And we're starting off, this is a strong acid, so we're going to start off down in this corner again, have that same sort of behavior going up like that. As we add more and more base to the solution, and we're using up those hydrogen ions, there'll be a point where the number of hydrogen ions is equal to the number of hydroxide ions in the solution, but that point is for only that first hydrogen leaving. Okay? So we're looking at the point where this stuff is associating, making this, and there's an equal number of these hydroniums and hydroxides in the solution, but from this dissociation, not from this one. And so we have an equivalence point here. And then you start to tilt over again. But here's what happens. There's a second equivalence point going along with this dissociation of hydrogen. Or in the case of the Arrhenius way of thinking about things, this dissociation of hydrogen. Okay? So there has to be a second equivalence point where these hydrogen ions or these hydronium ions are equal to the number of hydroxide ions. Now that's not the same hydronium or hydrogen ions as we had in the first reaction. This is a second reaction. So when the number of hydrogen or hydronium ions is equal to the hydroxide ions from this second reaction, then we're going to have that second cliff face there. Okay? And there is also in the middle of that, or the steepest point in that, is an equivalence point. Now, if you're taking calculus, you know that whenever you have a steep curve like this, you get a kind of a steep peak in your first derivative. So if we were to do a first derivative of this, we get a peak here and another peak here, because it's the point at which the line goes vertical that you have the steepest peak on a first derivative. And that actually helps us to find those equivalence points. So calculus comes into play when using these acid-base titration curves. So that's what happens with a diprotic strong acid. Strong, you can tell it's strong because we're starting down here in the corner, very low, having the sweeping sort of behavior here. Diprotic because we have two equivalence points, so we know there are two ionizable hydrogens. So let's give you a chance to practice now. Here's the problem I want you to do. Write and label all the dissociation equations. Write and label all the dissociation equations for chloric acid, and then draw a predicted titration or pH curve for that. So here's how this is going to work. Chloric acid has the formula HClO3, and here's how we know. There's no hydro prefix. This is not hydrochloric acid. If there were a hydro prefix, we would know the acid is binary. But because there's no hydro prefix, we know it's not binary, and there's a polyatomic ion in this acid formula. So chloric has to come from a polyatomic ion and we put hydrogens on there. In that situation, the IC ending on the IC ending on the name of the acid comes from the 8 ending in the polyatomic ion. So we're looking for a chlorate ion, and we're going to put hydrogen ions in the front to make an acid. So this is the chlorate ion. It's one of the ions that in honors chemistry you're supposed to memorize. Now then, if we're going to write an Arrhenius dissociation equation, where we take that chloric acid formula and just undo what we did up here to make the formula in the first place. Chloric acid, it's aqueous, we're going to put it in water. The hydrogen ion comes off and is dissolved in the solution, so we've got a hydrogen ion here, and the chlorate ion is by itself because once the proton leaves, that's what we have left. And so that's what you should be writing and labeling for an Arrhenius dissociation equation. If we're going to write the Bronsted-Lowry equation, then we're going to start with that same chloric acid, but instead of the hydrogen coming off and just ending up sort of floating around willy-nilly in the solution, it actually goes and joins up with another chemical species, in this case water, since we're just dissociating it. Hydrogen ions come off, join up with the water, we make H3O. When the hydrogen comes off, what we have left is the chlorate ion, and there it is. So this is the way we'd write a Bronsted-Lowry dissociation equation. Now, for the titration curve, or pH curve for this is a strong acid, and the way that you know it's a strong acid is this. If there are 2 or more oxygens more than the number of hydrogens, then this is a strong acid. So for acids that contain oxygen, called oxyacids, if there are 2 or more oxygens greater than the number of hydrogens, you can assume that to be a strong acid. Conversely, if we were talking about binary acids, acids that are made of just 2 kinds of atoms or 2 elements, like hydrochloric acid, HCl, then it would be a strong acid if and only if the anion was one of the halogens other than fluorine. So hydrobromic from the chlorine, hydrochloric from the chlorine, hydrobromic from the bromine, hydroiodic from the iodine. Those are the 3 halogens we're talking about that form strong acids with a hydrogen on the front. So since this is a strong acid, we're going to get this beginning behavior where we start very low pH and sweep up. Since we only have 1 ionizable hydrogen, we get a single Cliff face here, okay, and not 2 of them. And so this is the behavior we're looking for. So when you label this, you're going to label it then as an acid titration curve. Now, you could say an acid titration curve for chloric acid. That could be the title. But we've got chloric acid down here, so that would work for this one. You have pH, 0, 7, 14. That's the range we're talking about. Adding base solution down here, and where the equivalence points might be located. And where the equivalence point might be located. All right. So that's our equation then. So that's the answer to this practice problem. We're going to move on now and look at some weak acids. What's the behavior of a weak acid? So one of the weak acids is acetic acid. And acetic acid is a combination of the acetate ion, CH3, CO2 negative, and a hydrogen ion on there to neutralize the negative charge. This hydrogen ion has a positive charge and neutralizes that negative charge. So we're going to make CH3, CO2, and we can put the hydrogen on the front as if we're writing the formula for a non-organic acid, or the hydrogen can go on the back as if we're writing the formula for an organic acid. Let me explain that just a little bit. Go back and review a little bit about organic formulas. So this acid, if we're writing it like an organic acid in a complete structural formula, we'd have a CH3 group. The carbon here is bonded to this carbon with a single bond. This O2 means that there's a double bond to an oxygen. and then another oxygen over here, and the hydrogen is actually attached to this oxygen here. And this is the hydrogen that leaves when we acidify, or when we put it in water and it dissociates. If we're writing the formula for this, as if we're writing an organic acid, then we'd write CH3, CO2, H, the H going on this end because it actually attaches to this group here. This is the carboxylic acid group, okay, or a carboxyl group. This is a carbonyl. You can think of this as being an alcohol, and a carbonyl next door to an alcohol is a carboxylic acid group or a carboxyl group. Well, really with a hydrogen on there, it would be a carboxylic acid group. Just this part itself here is the carboxyl group. Now, let's write the dissociation equation now. So here's our acid. I'm going to write it in this form. And we dissolve it in water. And using the Arrhenius idea, we're going to get hydrogen ions. And then we're going to get those same carbonate ions. That we built the acid structure from to start with. The only problem is this is a weak acid, so it doesn't dissociate completely. At least that's one way to think about it. In fact, when we say it doesn't dissociate completely, what we really mean is the forward reaction, for every forward reaction, we also have a reverse. What we really mean is for every forward reaction, we also have a reverse. What it really means is for every forward reaction, we also have a reverse reaction. So this right here is breaking up into these things, but these things are reforming to make this. And so there's a point at which the rate of the forward reaction equals the rate of the reverse reaction, and we have an equilibrium or a balance there. Okay? If we're going to write this in terms of the Bronsted-Lowry theory, then we need our acetic acid. And we need a water molecule for the hydrogen ion to go and join up with. And we get hydronium then. That's a Q. I'm kind of making a mess of it there. And then an acetate ion. Again, there's a forward reaction and a reverse reaction. If we're going to write an acid titration curve for this, so this is for acetic acid. We'll put acetic acid here. So we're starting with a concentrated solution of acetic acid. We're adding a base solution. Now, this acid here is never going to be a strong acid. Yes, never going to be a strong acid. It's always going to be a weak acid. So we can never get all the way down to a pH of 0. We've got to start somewhere above it. And then what happens is we have this really long plateau. What's going on with that plateau? Let's go back to our original equation over here. Every time we make one of these hydrogen ions, we are reacting that hydrogen ion with the hydroxide from a base. Going back to our original discussion of Arrhenius acids and bases, here's an Arrhenius base. We're making hydroxide ions. So every time we form one of these hydroxide ions, it's reacting with the hydrogen ion. So this is being taken out and joining up with the hydroxide ion and forming a water molecule. So the hydrogen ions are being taken out of the solution because it's being caused to form, with the addition of this hydroxide, a water molecule. And because we have an equivalence point and a point of equilibrium where one side is balanced against the other, every time we take out something from this side, the new equilibrium is established. Some more of this is going to break up and form more of this. And we get an increase in this because this is being taken out. So the more amount of this increases, the amount of this decreases to keep that balance going on there. So when we look at that curve again, while we're adding more and more base is being added here, okay? But as we add more base, the base isn't changing the pH because the hydrogen ions are being taken out of the solution. Okay? And we're making more of this stuff and more of this stuff and more of this stuff. So it's a buffering region that we have here. There's no change in the pH or no significant change in the pH as long as we have more of this dissociation going on as we take more hydrogen ions out. Eventually, we'll put in enough hydroxide ions, we'll break up most of these things, and the equation or the curve starts to go upwards, and we'll get the traditional acid-base titration curve. The equivalence point is somewhere up here. Now, it's not always true, but most of the time with these weak acids like this, your equivalence point is somewhere above 7. So that's what would happen with a weak monoprotic acid. We call it monoprotic because there's only one ionizable hydrogen here. Even though there are 3 hydrogens in the formula, only one of those is in a position on the molecule to be broken away or dissociated. So it's a monoprotic acid. All right, let's look at some generalities now that have to do with the Bronsted-Lowry theory. So in our Bronsted-Lowry equations, we had an acid, hydrogen ion leaving and joining up with water and forming hydronium and some kind of anion. Depending on the acid, we always form an anion. So here's our acid, water, hydronium, some kind of anion associated with that acid. Acid, water, hydronium ion, and some kind of anion associated with that. Acid, water, hydronium, and the anion is associated with this acid. So in general then, we can say that a Bronsted-Lowry acid behaves in this way. We have a hydrogen ion attached to some kind of anion. That's going to react with water to form hydronium, and when we remove that hydrogen ion, what we have is an anion with a charge that's 1 more negative than the original acid had. And when I say it that way, I mean it because of things like this, where we started out with this formula, which had a negative charge, so the anion has 1 more negative charge than we started out with this acid here. Okay, so that's a general formula for the Bronsted-Lowry theory of acids and bases. If we were doing the Arrhenius theory of acids and bases, we wouldn't have water as part of the formula. We might put it as part of the arrow just to show that this is taking place in water. And so what we're forming then in the Arrhenius theory is hydrogen ions, and we still have that anion. Okay, if we have one of those weak acid reactions where we have a forward reaction and a reverse reaction going on, then we'd write this Bronsted-Lowry reaction in this way. And this is the real only difference here in this general formula, is that there's a forward reaction and a reverse reaction creating this equilibrium. The point at which this reaction, the rate at which this reaction is going forward equals, there's a point in time where the rate of the forward reaction equals the rate of the reverse reaction, we get this balance between the parts. And here we do kind of the same thing with the Arrhenius theory. There's some special terms that apply to Bronsted-Lowry reactions, however. Every Bronsted-Lowry reaction, and we define acids and bases in the Bronsted theory by what happens in the reaction. For every acid we have, there's always a corresponding anion that comes from that. So this is the acid, and this is the corresponding conjugate base of that acid. Why do we call it a base? Because this is an anion, and anions will easily accept protons. So since protons can join up with that, that makes it a base. If this is the acid and the hydrogen from this acid goes over here and joins up with water, well, that makes this the base. And once the base has accepted a proton, it becomes the conjugate acid of that base. It's the conjugate acid of that base. Now, why is it an acid? Because that extra proton on here isn't particularly stable. So those protons can leave and go back and remake the acid we started with in the first place. The hydrogen can come off of here and join it with its base. So this acid is an acid because the hydrogen can come off and join it with its base. Its base is a base because it can accept that proton. So those are some terms that apply to Arrhenius. Those are some terms that apply to the Bronsted-Lowry acid-base system. Acid, conjugate base, base, conjugate acid. You need to know that strong acids always produce weak conjugate bases. Strong bases always produce weak conjugate acids. You can't say anything else about the strength of conjugate acids and bases other than that. Only that strong acids produce weak conjugate bases, strong bases produce weak conjugate acids. We're talking about chloric acid in this problem. Chloric acid, there's no hydro prefix. So since there's no hydro prefix, this must be an acid that's built on the structure of an oxyanion. Okay, so there's some oxygen in the anion. So there's chlorine, we know that from the ClOR, and there's some oxygen on this. Okay, the ic ending here, then, in the absence of that hydro prefix, the ic ending means it came from a chlorate ion. And the formula for chlorate is ClO3, 1 negative. And I only need one hydrogen ion to neutralize that, so the acid formula is HClO3. There's chloric acid. Okay? So what I just did to build this formula is going to be undone when I write the dissociation equations. I'm going to start with the formula for chloric acid. And when I'm writing the dissociation equation in the Arrhenius form, I'm putting it in water, and the hydrogen ion simply comes off. So I'm undoing this. And we have a chlorate ion over here. Okay, so there's the Arrhenius dissociation. Dissociation just means it's an equation that describes the breaking up of something. Okay? Like when you associate with somebody, you hang around with them, right? When you disassociate with them, you stop hanging around with them. So that's what's happening here. Okay? Dissociate means the same thing as disassociate. Okay? All right, so then if we're using the Bronsted-Lowry way of thinking about things, then the water is not just sort of the environment this is happening in, it's actually part of the equation. And the hydrogen ion from this acid is going to dissociate from the whole formula, from the whole structure, and go over here and join up with this water molecule covalently bonding with a lone pair of electrons on the oxygen. And we get this hydronium ion. And we get the anion that's left over. And so this is the Bronsted-Lowry dissociation equation. And then to do the pH curve or titration curve, we have concentrated chloric acid solution. We're adding to that base solution. We're looking at what's happening to the pH as a result. 14 being the top, 0 not necessarily being the bottom, but we're going to start at 0. And 7 is the point of neutrality in the acid-base idea. It's neutral when it's at 7. So here's pH over here. And since it's a strong acid, it's going to start like this. Since it's monoprotic, that's to say only one hydrogen is removed, we get a single cliff face, and we get an upper plateau. Excuse me. Gracious. So let's go back and look at the general form for all these equations. Yeah, you probably should label the equivalence point being right here. For strong monoprotic acids, it'd be right here. All right. Let's go back and kind of look at all these types of equations we have. With Bronsted-Lowry, hydrogen comes off, joins up with water, forms hydronium. And you always got some kind of negative part over here that's left over after the hydrogen leaves. Even when we have this acid here that has two different protons that can be removed, you still have the acid, water, hydronium, and some kind of ion. The anion, what you have left over after the hydrogen leaves. That's the anion over here, okay? And then with this acid, when this hydrogen leaves, you get this anion, okay? So what we can do is come up with a general idea of what an acid is by writing an equation that sort of takes into account all these different structures and all these different formulas for acids. If we're saying that this part here, and here, is all represented by A negative, or the anion, then the acid formula itself can be represented as HA. Now, since in the Bronsted-Lowry system, HA is always reacting with water, and every time we react HA with water, we always get hydronium. We could call this a general formula for a Bronsted-Lowry acid, or a general formula for the dissociation of Bronsted-Lowry acid. What?
Is that A negative included into the equation, or is it to the side?
Say again?
Is that included into the equation? That's to the side.
No, this is actually part of the equation over here. Okay? A negative is the anion that you get that comes off of the hydrogen. Okay? So there's no acid anion that has just A. I mean, it just doesn't exist. This is just a symbol that represents all the anions in all of these dissociation equations. Okay? Or any anion. What?
What did you call that? A general equation?
Sort of a general equation. Okay? Let's go back one more then and look at Bronsted-Lowry and do the same thing. I'm sorry, not Bronsted-Lowry, Arrhenius, and do the same thing. So with Arrhenius, we just simply say it's HA, and it becomes H plus and A negative. Okay? And let's go back to Bronsted again. Bronsted-Lowry a minute. The way that we think about the behavior of acids and base behavior in this Bronsted-Lowry system, every acid forms some kind of anion, right? Turns out this anion can accept a hydrogen ion, making it a base. If it'll accept a hydrogen ion, it's a base, correct? Okay? So for every acid you have in a Bronsted-Lowry dissociation or neutralization, there's always a conjugate base. And the conjugate base is always what you get when the proton comes away, or leaves, or dissociates. Okay? And then in the Bronsted-Lowry way of thinking about acids and bases, the theory, you always are reacting with some kind of base, and the water is the base because it's accepting a proton. That's the definition of a Bronsted-Lowry base. If it accepts a proton in a covalent bond, it's a base. So this is a base. And this stuff right here is what you get with water when the hydrogen attaches itself to the lone pairs of electrons on the oxygen, forming a covalent bond. But this hydrogen, this proton, one of these protons can leave this. Just like it joined up, it can also leave it, which makes this an acid. So this is a conjugate acid to that base. So every acid in the Bronsted-Lowry system has a conjugate base. Every base has a conjugate acid.
Is that what the Arrhenius acid is doing?
No, we don't use those terms for Arrhenius. But Arrhenius being a simpler idea, it's a lot of times a lot easier to kind of figure out what's going on by thinking about Arrhenius. But it's also necessary to think about it in terms of Bronsted-Lowry because so many things that behave like acids and bases would not fit the Arrhenius theory. Okay? So those terms you need to know. Acid, base, conjugate acid, conjugate base. Now, turns out, from practical experience, from experimentation, we know that strong acids always produce weak conjugate bases. Strong acids always produce weak conjugate bases. Strong bases always produce weak conjugate acids. So far, we've talked about nothing but strong acids, and strong bases for that matter, okay? What about weak acids? Well, it turns out this species right here, this is our acid, that's our conjugate base. Because when we remove the hydrogen ion, what remains is the base, conjugate base, okay? Since this second hydrogen can come off of that, this conjugate base is also an acid. All right, because you can remove another hydrogen ion, it must be an acid. You with me so far? Okay? So here's an acid, there's a conjugate base. Here's a base, there's a conjugate acid. Here's an acid and its conjugate base. Here's a base and its conjugate acid. Does that make sense? This is the strong acid because it dissociates completely. Okay, so that's a weak base. This is a weak acid, and it's a weak acid because it doesn't just go in this direction. In other words, a weak acid doesn't completely break up. That's where we think about it. But what's really happening is it can completely break up, but it doesn't all break up at the same time. What's happening is this hydrogen's coming off of here and forming hydronium, but it's also true this acid is losing that proton and rejoining up with the sulfate to make this. So this reaction is actually going in both directions at the same time. And we were doing solutions in the last unit. We talked about equivalence occurring, okay, a point of equivalence occurring when the rate at which the reaction going in one direction equals the rate at which the other reverse reaction is happening. There's a balance going on there, okay? And so this applies to the same idea, this same concept of equivalence, a dynamic equilibrium, where there's a constant change. We're constantly breaking off this hydrogen, putting on this oxygen, forming hydronium, but constantly breaking off a proton from here, rejoining with the sulfate, and making this. It's going around and around and around, but if you measure the amount of this or this or this or this, as long as you don't change the conditions, the two sides would stay balanced all the time. A dynamic equilibrium, okay? And that's what weak acids and bases do. They form a dynamic equilibrium. So let's look at a weak acid, one that does not start with a strong acid, okay? You recognize this acid?
Is that why it's hard for weak acids and weak bases to dissociate more?
Is that why it's hard for weak acids and weak bases to dissociate? It seems harder because while they are dissociating, they're also reforming. And so it seems harder, yes. Okay? All right. Now this isn't carbonic. Carbonic is H2CO3. How about just this part of it? What's it called? It's one of the ions you're supposed to memorize, acetate. Okay? So if I put a hydrogen on an acetate, what do we call the acid? Acetic. Okay? This is acetic acid. Okay? If we were writing this in the way we would write it for an organic acid, and it is an organic acid, we'd have a carbon with 3 hydrogens on it, and that would be bonded to another carbon. So there's 2 carbons here, and then the carbon has 2 oxygens on it. One of those is double bonded. That's a carbonyl. Remember carbonyl? And this we would normally call an alcohol, except that an alcohol right next door to a carbonyl forms a carboxylic acid. And this is the ionizable hydrogen, the one that leaves and forms a proton. Okay? So if we're writing this as if it were an organic acid, we'd write it like this. This is the hydrogen that leaves. When we write it like this is the hydrogen that leaves. So this is the way of writing it as if it's non-organic. This is the way of writing it as if it's organic. Okay? In either case, you have to know which hydrogen is leaving. Okay? Which one forms a proton. Now, all of the organic acids are weak. That's just a rule of thumb for you. Okay? It also doesn't meet the rule for having a strong acid with oxygens in it, because it only has 2 oxygens, and you've got to have at least 3 oxygens to have 2 or more oxygens and hydrogens to make it a strong acid. Remember that? If you'll remember that rule, that'll kind of help you figure out whether you have a strong acid. It is not a strong acid. There's 2 ways to think about it to figure that out. Okay. So when we put this in water using this Arrhenius concept, we get hydrogen ions. We get acetate ions. But the reason it's a weak acid is that very little of these actually are broken up at any given point in time. At any given instant in time, you have a lot more of this than you have of these. Because while this is breaking up, these are reforming. And we have an equilibrium being established here. Okay? We have a dynamic equilibrium. The rate at which the forward reaction equals the rate at which the reverse reaction is occurring gives you that point of equivalence, okay, where there's a balance there. Okay? Like class change at our high school. Okay? People are walking up and down the hallway, but the number of people in each end of the hallway stays about the same. Okay? That's what's happening here. All right? Now that's what a weak acid does. The reason it's so hard, as JJ was asking about, the reason it's so hard to neutralize a weak acid is that whenever I introduce sodium hydroxide or any other kind of base to this, what I'm doing is associating the hydroxides. Okay? Potassium hydroxide, sodium hydroxide, they give you hydroxides in the water. That hydroxide wants to join up with this hydrogen ion. They want to join together to form what? Water. Okay? Which means you're neutralizing it. There's no more acid or base there. Okay? So as I add more and more base to it, I keep pulling these out. It's like I'm scavenging those hydrogen ions. I'm pulling them out of the solution because they're joining up and making water. Okay? Well, this equivalence means the amount of the stuff on this side wants to stay the same ratio, in the same ratio as the stuff on the left side. Okay? They want to stay balanced out. Well, if I pull these out, I've got to increase those. So more of these break up. Then more hydroxides are used up, using up the hydrogen ions, more of these form. More hydroxides are used up, taking up the hydrogen ions, more of these are formed. Until finally you use them all up, then you can change the pH. You understand the picture here? Can you see what's happening in your head? Get it? You understand the dynamics going on here? All right, that's why it's so hard to neutralize, or why it takes so much extra base to neutralize a weak acid. Yes?
Where did the OH come from?
We added some kind of strong base to the solution. We tried to neutralize it. Okay? Now, let's write the Bronsted-Lowry version of this, and I'll show you what that looks like on a pH curve. Okay? So here's our acetic acid. And we're going to react it with water. Hydrogen is going to leave the acetic acid, join up and covalently bond with the lone pairs on that oxygen. We make H3O, or H3O plus hydronium. And what's left over after the hydrogen leaves is the acetate ion. Acid, conjugate base. Base, conjugate acid. But it's a weak acid-base system. So while this is constantly happening going in this direction, it's also true that the reverse is also happening. And very often we'll write these kinds of equations with a longer arrow pointing toward the side that we have the most concentration of. So if I were writing this with a short, I would write this in that way. If I were writing this in that way, I'd have a short arrow going this way and a long arrow going this way, because you have a lot more of these than you have of those. Okay? At least under normal conditions until you start to neutralize it. When you start to neutralize it, then you're changing conditions. You're changing conditions, you're reestablishing a new equilibrium, which is what a dynamic equilibrium does. That's what Le Chatelier is all about. Okay? If I change the conditions under which this equilibrium is established, the equilibrium will be reestablished at some new balance point. Okay? So, if I have a titration curve, 7, 14, 0 pH on this side, I have concentrated acetic acid solution, I'm adding base. We never quite get to 0. Okay, I never quite get to a pH of 0 because I can't dissociate enough hydrogen ions to get there. Because it's more of this stuff than of that stuff. I can't dissociate enough hydrogen ions to get a really low pH. And so our pH curve actually starts somewhere above 0. And then because as I add more base, adding base here, to try to neutralize this, I'm constantly making more of this stuff. The base is constantly being soaked up in this reaction, making water. I get this really long plateau here before it finally starts to curve upwards and finally get that traditional, or what we're looking for in a pH curve or titration curve. And the equivalence point for these kinds of acids is almost always, not always, but almost always somewhere above 7. The point at which the number of hydrogen ions is equal to the hydroxide ions is almost always going to be somewhere above 7. Okay? And this region here, where it's taking all that extra hydroxide ion to neutralize that acid in that region because of this dynamic that's going on here, this is called a buffer region. And buffers are the reason why your pH stays at about 7.4 in your blood. You die without buffers. In fact, if your pH gets a little too high or a little too low, you pass out. Here's the homework. Write the dissociation equation and predict a titration curve for hydrofluoric acid.